I feel really privileged to be invited back here. There are so many speakers who I really respect, and I feel like the quality of information here is really high. And as I tell people when I come here, it's because there's so many people who are doing really good presentations, and because everyone's got their laptops closed, and I look out at a sea of faces, not a sea of Apple logos, it forces me to raise the bar on what I'm going to talk about and how I present. And anyway, it's a real privilege to be here. Really appreciate it. So I'm going to talk about the magic that makes macOS volumes fast, right? That's the title. But first, I wanted to mention a saying that a friend of mine who's a car dealer mentioned to me maybe 20 years ago. He said, people buy horsepower, but they drive torque. So when they go to buy a car, they look at the specs and they go, this car has more horsepower than this car, therefore I'm going to buy this car. This car's better. But when they get in the car and they're like punching it because they're trying to pass somebody or they're on some curvy road, it's torque that matters. So I think the corollary with storage is that people buy speed, and what they really want is reliability. So the real title of this talk should be The Magic Which Makes macOS Volumes Fast and Reliable. And we're going to talk about fast, and then we're going to talk about reliable. And I think you're going to be impressed with the fast, but the reliable is what the meat and potatoes that you're really going to remember. So let's talk about fast. We're going to go over storage speeds, how they've improved over the last 5 years. We're going to go over PCIe Gen 4, and we're going to go over Thunderbolt 5, which is coming pretty quickly, and there's some things you should know about it. So year over year, storage speed increases. First of all, every storage device I'm talking about uses soft RAID. And we use soft RAID for all our enclosures that have more than 4 drives. The reason is it allows us to use the host CPU rather than a dedicated RAID processor for doing parity calculations and for doing all of the I/O scheduling and things like that. The host processor is like so much more powerful than any RAID controller you can get. It's just dramatically better. And when you increase the speed of your computer, your RAID performance gets even faster. So it's like automatic. It's like 3 years later, you've got a faster RAID box because your host CPU is faster. There's no hardware dependency, so if something happens to your enclosure, you can just take the drives out, put them in another drive. You can even put them in those little docks where you stick the drives in, they're connected. Anything will work. You can even take like one of our competitors' hardware RAID boxes, turn it into JBOD mode, put your drives in, soft RAID will just recognize it. And we have much better health tracking than a hardware RAID enclosure has because we're actually talking directly to the disk, not through a RAID controller. Lastly, as of macOS 13.3, there's no driver install. It just happens automatically. So you can take a soft RAID volume in any enclosure, plug it into any Mac in the world that's running macOS 13.3 or later, and it will just mount, and it will be full speed, and it will rebuild if it needs to. It's completely just like plug and play. I'm going to be using speeds that I'm going to be quoting. They're all collected with AJ System Test. I use AJ System Test because I find it really reliable. I can configure it to use 64 gigabyte test files. So a lot of the RAID controllers have built-in cache or have cache associated with them. And you'll see the performance really fast for like 2 to 4 gigabytes, and then it just stair-steps down by sometimes a factor of 3. By using the longer test period, that gets ignored. That gets sort of washed out. And these are the other settings I'm using, just so you know. I'm not cheating. I'm not doing anything fancy. I'm actually using the settings that I think are the hardest for a RAID volume to actually perform well at. So in 2018, we introduced NVMe blades were just coming on the market. We introduced this product called the Thunderblade, which has 4 NVMe blades in it, and Thunderbolt 3. And I was at NAB demoing this on an Intel MacBook Pro. Now remember, Intel MacBook Pro has 2 Thunderbolt ports on either side, but each pair of Thunderbolt ports is connected to one Thunderbolt controller and has 4 PCIe lanes coming in. So you have 4 on the right side, 4 on the left side. So I plugged in 1 Thunderblade on each side, and I was getting about just over 4 gigabytes a second. Well, in 2018, this was pretty phenomenal. And I was sitting there at the end of the edge of our booth, and as people would walk by in that sort of glazed state people are in when they're at a trade show, I would say, hey, check this out. And they'd look at it, and then they'd look at it and do a double take and go, wow, 40 gigabytes a second. I had people accusing me of running a video. Like, hey, you just made an animation. I said, no, it's the real thing. So a year later, the 2019 Mac Pro came out, and we developed a card called the Excelsior 4M2. It's got 4 blades. It's basically a Thunderblade with on a PCIe card, and we were able to get 6 gigabytes a second out of that. That seemed like a major step forward. Hey, this is really cool. We're now at 6. So fast forward to 2022, and Apple introduced the Mac Studio, and I said to Mark, I said, hey, you know, we should test 4 Thunderblades on this. See how fast it could go. So he plugged 4 Thunderblades in. It's got, you know, we have the low-end one because we're saving money. So we have 4 Thunderbolt ports in the back. Each one is its own 4 lanes, 4 PCIe lanes. So each one gets the full bandwidth from 2.8 gigabytes a second. So Mark made a 16-blade RAID 0 volume, and we were seeing over 10 gigabytes a second reading and writing on this device. I thought it was pretty awesome, you know, a non-expandable machine with 10 gigabytes a second. Later in 2022, we came out with the Excelsior 8M2, which is an 8-blade NVMe controller, and we were getting 12 gigabytes a second on this. And this seemed like screaming fast, right? So this is a card that we designed with the future in mind. It's PCI Gen 4. Obviously, the 2019 Mac Pro is PCI Gen 3. So it's cool. It works really well. People were super happy with it. It was used for mixing all the audio for major motion pictures at the time. 2 of them were done on it. And it comes in size up to 64 terabytes. So fast forward to earlier this year when Apple introduced the 2023 Mac Pro, it has PCI Gen 4. And we all of a sudden, that same card, the same RAID software, in fact, the driver hasn't changed very much in the last 4 years, the same RAID driver, right? It's not the same as hardware RAID. It actually tracks with your processors. So the same exact hardware and software are running now at 24 gigabytes a second. And here's the AJA system test numbers. You can see AJA hasn't quite caught up with us because they clip the numbers when they're too large. We had this problem back with 2018 when we came out with 4 gigabytes a second. Blackmagic would sort of peg at 2 gigabytes a second. They wouldn't even report it correctly. We had a problem with AJA. We had to get them to improve their software so it could measure. It's like the gauge didn't go far enough. So yeah, this is the performance we get. We can run this for days and get the same numbers. Let's talk about PCI Gen 4. So PCI Gen 4 is double the speed of PCI Gen 3, which is sort of what you expect, 2 gigabytes per lane. Pretty awesome. But as we know with processors, when you increase the frequency, right, what happens with the heat and the power consumption? It goes way up. It's faster than linear. So you're going to see as we go forward, like that, the Excelsior 8M2 is a PCI Gen 4 card. If you put it in a PCI Gen 3 computer, you can just plug it in. It just uses the 75 watts that's available. If you plug it into a PCI Gen 4 computer, you need to connect up the auxiliary power cable because it's sucking so much current. So with power consumption comes heat, and it's something to keep in mind as you're moving forward onto PCI Gen 4 equipment. The other thing to keep in mind is the Mac Pro, although it has 2 16-lane slots and 4 8-lane slots, you actually only get a total of 24 lanes, Why is that? All the PCs, the Windows PCs have so many more lanes. Why does the Mac Pro only have 24 lanes available for slots? The reason is because you've got 8 Thunderbolt ports, and each one of those Thunderbolt ports has 4 lanes. So you've got 32 lanes associated with Thunderbolt and 24 lanes associated to your slots. And they're set up in 2 pools. So if you put a Excelsior card in one slot and give it the full bandwidth, you're going to see the full performance from it. If you put another card in, it's going to be sharing. So if you're doing something simultaneously to both cards, you're not going to get full performance. The other pool is Pool B. It's only 8 lanes. You'll see 12 gigabytes a second if you put the Excelsior 8M2 in there. Let's talk about Thunderbolt 5. Thunderbolt is really cool. It started with Thunderbolt 1. It's 10 gigabit a second. It then went to Thunderbolt 2, where all they did was double the number of lanes that were on the cable. Thunderbolt, the way I think of Thunderbolt is it's like VPN for your PCI bus, right? So VPN, as I'm sitting here on a computer, I get onto my VPN. It sort of tunnels my internet traffic halfway around the world. It pops up in Paris so I can watch TV Sync in Paris which is geo-blocked for me right now. So it's the same. You have PCIe. PCIe can only go like, well, what is it in metric? 200 millimeters. It can't go very far. So you tunnel it over this cable, and it pops up in your enclosure, and then it's PCI again. So as we go forward, you can see that Thunderbolt has gone from PCI Gen 2 to PCI Gen 3, and now it's PCI Gen 4. What did I say about PCI Gen 4? Oh yeah, it can use tons of electricity, tons of current, and produces lots of heat. So when we start looking at Thunderbolt 5 devices, you're not going to see a 5 gigabyte a second handheld bus-powered device. It's just not going to happen. There's way too much current required to run that speed. It's possible in like 4 years, if the chips get smaller, the feature size gets smaller, and they get more power, they use less power, then we might see it. But in the near term, you're going to see devices that are really fast that have fans, and you're going to see portable devices that are just as fast as we have right now. The key thing to know about Thunderbolt 5, aside from that, is it's literally twice as fast. So we're going to see more than 5 gigabytes a second. It supports more monitors. I think it's up to 8 monitors or 6. I can't remember. It's a lot of monitors on one bus. So if you're doing external monitors, it's really great. If you're doing really high performance storage, it's going to be really great as well. So you look at it and you go, wait a minute, 80 gigabit. Does that mean it's 80 gigahertz? No, it's not 80 gigahertz. First of all, we've got 2 channels, so you need half the speed for that. And more importantly, they use this really cool encoding called PAM3, pulse amplitude modulation. It's the same encoding that's used for 100G Ethernet. And what this means is instead of having a high and a low, a 1 and a 0, you actually have 3 levels. You have a high, a 0, and a low. And so you've got 3 levels, which means instead of high and low, which means every pulse is is a base 2 number. 3 levels means every pulse is a base 3 number. So, well, how do you deal with base 3 and base 2? We're dealing with bits on this wire. Well, the people came up with PAM3 did something really cool. They put them together in pairs. So 3 to the 2 is 9, right? 3 times 3. So 9 is very close to 8. In fact, it's slightly larger. And 8 is 2 to the 3rd. So you can take 2 3-bit numbers, base 3 numbers, and have 3 base 2 numbers, right? So every 2 pulses then gives you 3 binary bits. And this allows you to have a lower clock frequency and have to deal with, you're not like pushing the envelope quite so much in terms of how fast your cabling has to be able to support, how fast your processors have to be, how fast your controllers have to be. Let's talk about Thunderbolt cables. What's going to happen with Thunderbolt 5 with Thunderbolt cables? Well, the good news is, so this is just a summary of Thunderbolt cables that you might have in your drawer. The USB ones, obviously, you don't want to use. The passive cables, which are the ones which don't have a number on them, Intel has said that all passive cables, Thunderbolt 3 will work on Thunderbolt 4 and Thunderbolt 5. So passive cables usually are under a meter, often they're 0.7 meters. So you should be good to go with those. There's one caveat I'll tell you in a second. Thunderbolt 3 active cables, with the little 3 on them, they're 2 meters. I say don't use them, and I'll explain why in a second. Thunderbolt 4 active, if you plug them in, your Thunderbolt 5 bus will drop down to Thunderbolt 4 speeds. And Thunderbolt 5 active is going to work on everything. They're not out yet, obviously, but they will be. I think that the rollout for Thunderbolt 5, Intel says it's going to be available the beginning Q1 of 2024. I would suspect, knowing Apple, I don't know anything internal. I'm not magician or anything. I would expect that WWDC in June of 2024 is when we'd see a Thunderbolt 5. It's just a guess. And keep in mind also that Apple has this habit of, like when they introduced Thunderbolt 4, they didn't really introduce Thunderbolt 4 because they didn't support 2 4K monitors, which was a requirement for Thunderbolt 4. So the first Macs with Apple Silicon supported hubs but didn't support the monitors, therefore they couldn't call them Thunderbolt 4, so they just call them Thunderbolt, hey, but you can use a hub. It's sort of a mess. You'd think that Apple would be on board with the standard since they're part of the whole push for Thunderbolt, the major vendor, but they want to do it their own way. So let's go over cables in a little more detail. USB might work on Thunderbolt, might not. It's going to be slower. It's going to be much less reliable. Basically, don't use it. I've seen a couple of our test computers hooked up with Thunderblades and the USB cables, and then people are wondering why they're going slow. Duh, it's just there's no symbol on there, right? The Thunderbolt passive cables, avoid the 2-meter passive cables. They were shipped for a while, but they actually downgrade your performance to half of Thunderbolt 3. So they're running at 20 gigabit a second, not 40. So the maximum performance you're going to see is like 1.2 gigabytes a second. It seemed like screaming like 5 years ago, but now not so much. Thunderbolt 3 active cables, I say don't use these. They have the little 3 on them. The problem is if you plug them into a USB device, you're only going to see 40 megabytes a second. This is like ridiculous, right? We had one of our customer support people stumped for 3 weeks on this very thing. How come when I plug in this device, I'm only getting 40 megabytes a second? I thought maybe it was a drive problem. It just made no sense whatsoever. And one of our really brilliant people in the hardware lab said, oh yeah, it's because Thunderbolt 3 active cables only do USB 2. So that's floppy disk drive speed for those of you who remember using floppy disks. I'm dating myself, I know. So let's talk about reliability. We're done with speed, right? We know it's going to be faster. We know it's going to be really cool. We know it's going to consume a lot of heat, or a lot of electricity and make a lot of heat. We're going to go through protecting system volumes. We're going to talk about KEX. We're going to talk about bit rot, a revisit for what I talked about back in 2019. We're going to talk about how far we've come in protecting people from losing their volumes and the possible one remaining problem that I know of at the moment. I'll explain that. And then we'll go through a real-life example of someone losing their volume. So protecting our system volume, what do I mean by this? Apple's on a quest to make the Mac as malware impervious as possible, and they've done this by repeatedly locking down the operating system. And the current version of the operating system is locked down using a system called signed system volumes, and we're just about to go into a deep dive on that. But first, I want to talk about APFS. I think it was in 2019 I talked about APFS, or maybe it's 2018. Anyway, the key thing you need to know is that every piece of metadata, by that I mean data about the file system, about the individual files, their creation date, their modification date, their size, anything like that, any block of that is protected by a checksum. And it's not, we're going to talk about checksums, we're going to talk about cryptographic hashes. They're sort of similar, but they're sort of not. The requirement for a checksum is that you can detect when some bit has been changed. Some part of it has been changed. The requirement for a cryptographic hash is you can not only determine where it's changed, but that's really hard to generate data that creates a given value, a given checksum or hash value. So with a checksum, if you wanted to change some data, you could like possibly pad some extra data on the back and figure out exactly what order, what type of data you had to have in that little extra block to get the original checksum, right? So you could have two things with the same checksum, and you could make the change you wanted and add a little bit and end up with a checksum that was original, the same as what you originally started with. With a cryptographic hash, by design, that's not possible. If you make a change, it's computationally way too hard to actually figure out what extra data you need to add on the end to get the same hash value. And that's important if you're trying to prevent somebody from modifying a system file and then putting it on your computer and putting a backdoor in it. So here is my little diagram of there's a tree here. It's part of your system file. I didn't make the whole thing, but just an example, each directory has the metadata for what it contains, the files and the other directories it contains, and then it has its metadata with the associated checksum. Signed system volumes. I got interested in this because I started looking at disk utility, and there's like this snapshot. What the hell's the snapshot doing there? Right? It's sort of a stumper. You've got this, what Apple's now calling a volume group. I'm into coffee, as are other people in the audience, and my favorite drink is a cortado. So I'm sitting there, and that's the name of my boot volume. So I'm sitting there, and I'm like, I'm booted from a snapshot. What's going on? If I look in disk utility list, I see my system volume. It's right there, but you'll notice that it's not mounted, right? It's sort of weird. I'm booted, but I'm not mounted. It turns out we're booted from the snapshot that's right based on that, which is right underneath. And I think it was macOS 11, Apple introduced the data volume and the system volume, right? So there's a data volume and system volume. And my data volume is part of that same volume group. It's up here. It has all my data on it. So what Apple does in the file system is they sort of push these two together, right? They push the data volume into the system volume. And what they do is they mount the data volume at system/volume/data. So it's sort of like a little bit of magic that's happened there. How is this magic happening? You know, how is it that we're able to have a volume that's actually made of two volumes, and part of it's readable, and part of it's a snapshot, and part of it's read-writable? Like, it's sort of weird to wrap your head around it. And it turns out that it uses a concept called firm links. Now, we know that with symlinks, you've got a symbolic link to some other place. It can be on another volume, another file system. It's like an alias, right? It's got the path name embedded in it. You double-click on the alias, poof, you're over there. Hard links are what Time Machine used to use, and it's where in your directory structure, you've got a pointer that points to an object that already exists. So it has to be in the same volume, and it's actually inside the file system. It's not an alias, and you've got two separate entities in your file system, but they actually both point to the same metadata that then both points to the same extents and the same on-disk storage. Right? So Apple came up with this idea of firm links. With both of these things, once you get to the destination, you can't do cd ... and end up going back, right? You just go back to the parent of whatever object you were in. So with a symlink, if you go to a server and then you go up one directory, let's say it's a volume on a directory on a server, then you just go up one directory. You don't go back to where you started from. A firm link is different. A firm link is like a hard link, except that it allows you to go backwards. So if you go one direction, you can cd, and you don't go to the parent of that directory. You go back to where you started from. And this allows them to do all sorts of really cool things with embedding parts of the data volume in the system volume. And as an example, this is where your firm link list is kept. And it's really interesting to go nosing around there and see what is in there. And you'll notice that the applications folder is firm linked. Wow, that's sort of weird. Why is the application folder firm linked? It makes no sense. But then when you dig a little further into it, you can say, okay, I hope this isn't too small. You can see that over here we have system applications, and we have books and calculators. All the apps that Apple ships with, they want locked down. They don't want anyone messing with these. These are actually files that you can't modify, you can't delete them, you can't do squat with them because they're on your snapshot. And all the files over here are the ones that I copied in. So I've got 1Password, AJ System Test. I use Qobuz for my music. I use Pixin for editing pictures, yada, yada, yada. I love OmniFocus and OmniOutliner. It's also got Xcode in there. And you'll also find Safari in there. And Safari's in there because Apple wants to be able to upgrade Safari without forcing you to do a complete OS update. So they stuck Safari in the Applications folder. So the thing, remember I was talking about cryptographic hashes? Well, cryptographic hashes are the magic that makes these signed system volumes work. And a cryptographic hash is just, it's made on the contents of a file, or if it's a directory, it's made from the checksums of all the cryptographic hashes of all the contents of that directory, plus its own metadata. So the difference between these cryptographic hashes and what was used before, which was code signatures and code notarization, is that code signatures only work on executable code, right? So you can protect all your executable code, but you can't protect the script files or the other files that couldn't be signed, the configuration files that Apple ships. So by making all this other data protected by these cryptographic hashes, literally every single file has a cryptographic hash with it. And let's go over now how we create a bootable volume on macOS 13 and 14 with signed system volumes. So obviously the first step is you write in the files, right? You set up the volume the way you want to do it. Then we recursively go through all the files in this volume, the system volume, and we create cryptographic hashes for them. So we're starting from the leaf nodes, the very end, and we work up because every time we go from one directory to its parent, the parent has to be able to scan and get all the cryptographic hashes for the contents of that folder, right, or that directory, to make its own cryptographic hash. And we just sort of walk down the tree. We end up at root, and we have a cryptographic hash for root. And the cryptographic hash for root is called a seal. And the seal is a unique number. I believe they use SHA-256 for all the hashes. So that seal is a unique number. And Apple knows what files you have on there, and they know what the metadata is for them. They know the sizes and the creation date and all that stuff. So they have a value in their server somewhere in Cupertino or wherever it is, and they know that for macOS 14.0 build something, 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 the seal is this. So as you go through this process of creating all these cryptographic hashes, the next step is the cryptographic hashes are kept in a B tree. The B tree is in the metadata for the volume. And the last step is the installer goes, okay, does the seal agree with what Apple says it should be? And that's why you need to be connected to the internet, by the way, when you do an install, because this check has to happen. And if it doesn't happen, then the installation stops, right? So assuming it matches, then we take a snapshot of the volume and you restart. And as you restart, there's magic that happens. The magic is every time you restart, the cryptographic seal gets checked against the valid value for that build. And as long as they're correct, you can start up. And if not, if you've monkeyed with some file and you've figured out how to get everything to work and you've created a new snapshot, it's going to have the wrong seal. And the boot system is going to say, whoop, you're out of luck. And you get the wonderful, I can't boot from this user interface. So the other magic about this is that if there was some piece of malware that was actually able to write to the raw disk, I don't think this is quite possible, but someone could reverse engineer the secure enclave and figure out how to do it, or you could have booted from another machine and and actually, or another startup volume and actually touched some part of the storage. If some piece of code modified the backing store, the actual raw disk, with, say, your kernel file or your APFS file system text or something else, then it would fail. And the reason it would fail is every single read from the system volume and from the signed system volume goes through, assuming it's an internal boot volume, goes through the secure enclave either in the T2 chip or built into the Apple Silicon chip. And if every time a read happens, it reads the entire file, calculates the checksum, and compares it with what's in the tree. And if it doesn't match, the read fails. No data, error comes back, and the system says, boop, I can't boot. So this is the way of protecting at use time exactly the contents of each and every file in the signed system volume. I think it's pretty magic myself. It's sort of got me, I get excited about things like this. I can't help it. So we're going to take a brief pause, because I know it's a lot to absorb, and I don't want to totally burn you guys out. Every time I go somewhere, I always love searching out good food. And so I think last time I talked about Bove, which is the pizza place about 3 minutes walk from here. We went there last night for dinner. It's just as magical as it was last time. Many years ago, I discovered De Matteo. I think there are 5 of them here. If you're into really wonderful espresso-based drinks, they have it figured out. They're doing a light roast coffee, so you get all those wonderful floral and citrus notes in your coffee. There was one this morning I had, which they had tried. They said it had a sort of green apple taste, and it did. It was really unusual. So I really recommend that you try it out if you're around this afternoon. It's a great place to have sandwiches as well. This is the one I go to, the one in the passageway pretty close to the hotel I'm in. This morning, I dragged Sebastian out in the rain to this place because, like everybody else in the world, I was making lots of bread during the pandemic. This is a sourdough bakery. They often apparently have a line out the door. There's a tiny, tiny place, and they have 4 people working in there, and they are cranking out the bread. And I remember discovering it after my talk in 2019, and I had to go back there. It's wonderful. They're open in the morning. I think they often sell out. They have little rolls. They make sandwiches for you and things like that. I really recommend it. It's about 20 minutes walk from there. And the really funny thing is that we were up there this morning, but last night I dragged Sebastian off to another place that was literally around the corner. It's a chocolate place called Starman Billa. And it's not just a chocolate store, it's actually a couple of people who are so passionate about chocolate that they import the raw cacao beans, they roast them there, they winnow them, they conch them and make the chocolate, and they just make bars. You can now get their bars all over Gothenburg in the museums and some stores. It's really a class act. I love it. And you can sort of peer through, and their storage, their shop, their factory is like literally this large. It's tiny, but they're just like, they have all the right equipment in there, and most importantly, they have a passion. And you can smell it when you go in there, you can taste it. Sebastian obviously was really happy when he had his hot chocolate there, which was made from melted chocolate, not from cocoa powder. It was a pretty ethereal experience. But as I say, it was literally right around the corner, so it was funny this morning to be at the bakery and realize we could have just walked another 100 meters and avoided walking in the rain this morning. Okay, so let's go back to storage. See, was that a good break? I know when I'm in a conference and someone's like about minute 35, I start to wander. And I thought, if everyone thought a little bit about food, we'd be good. Okay, so kex. I read over and over that kex are going to disappear. Oh yeah, soft RAID's going to be useless because kex are going to disappear. The thing I got to tell everyone is, go and look in system library extensions, which is where Apple puts all of its kex. There's like 170 kex in there right now. So you can tell that kex are going nowhere fast, right? They're here for good. But what is happening is Kex in library extensions, which is where we've always put our Kex, the third parties have put our Kex before, it's the one place where kernel code is not part of the signed system volume, right? It's not protected, it's not verified when it's read. There's just a whole bunch of things that security things that don't happen if you have a driver installed there. So Apple is pushing third-party developers in one of two directions. They want you either to be using DriverKit, and DriverKit is the ability to put a driver in user space, like the original mock kernel that Carnegie Mellon developed in the whenever it was 90s, or they're getting people to move their drivers into system library extensions. So the problem with DriverKit is if anyone's used a product like MacCFS or LTFS, they rely on MacFuse, and MacFuse is open source, or it was originally open source. It allows you to have a user-level driver, and then all the calls sort of get piped through to the kernel through a process called user clients. The problem is that every time you go through to the kernel and come back from the kernel, there's quite a bit of overhead. You're like remapping memory, you're validating the call to come in because it's got to be safe, all this stuff. So it's not great if you need really high throughput. So we chose the route of putting our driver in system library extensions, and this is sort of a summary of what you get when you're in system library extensions. You're now protected by the signed system volume. You're part of that whole tree. Your driver gets, all your driver's files get validated on read. You don't have to reduce security on Macintosh with Apple Silicon. You don't have to allow the driver. It just loads up automatically. So with the software Kext, before macOS 13.3, we were in the old school where the user had to reduce security. They had to allow driver. If you got a machine that had a fresh install of macOS, you had to run, even though Apple installed a version of the driver, the version they installed only had Intel binary on it, not the ARM binary. So you had to run the software application, yada, yada, yada. As of macOS 13.3 and later, the driver's there. So all you do is plug in the volume, and it mounts, okay? You don't get all the disk monitoring stuff that comes with Software Monitor because Apple won't install that for us, but you do get the driver. You will get 24 gigabytes a second when you take your Excelsior card, plug it into a new Mac Pro. The other thing to keep in mind is that we're now sort of in lockstep with the macOS releases because we're part of the operating system, essentially. With macOS 13.3 through 13.6, it's software version 7.5 driver. With 14.0 for the next, like, I don't know how many months, it's going to be version 7.6. There's a weird thing that happens, though. Customers install this, and then they call support, and they go, hey, what gives? You know, the system report is telling me that this driver isn't any good. And this slide is just to point out that this is the SMB driver, and you can see it says it's not loadable, it has validation errors, it's not signed, it's incomplete, et cetera, notarized, unsigned. This is just system report not keeping up with the times, right? This is Apple's own driver, it loads fine. Likewise, the software driver, it loads just fine. Also, it has all the same errors. So if someone complains about it, just say, it's a problem with system report, because it is a problem with system report. I talked about bit rot in 2019. What is bit rot? Bit rot is this thing that everyone was like totally paranoid about because these people at CERN wrote this paper about how data stored on hard drives, if it was just sitting there, would magically change. And there was all this like people writing up articles in PC Week and everything else, PC Mag, and everyone was worried about it. And it didn't make sense to me because disk drives have always the actual physical sectors. At the end of the physical sector is a block of data that is a checksum, and it allows them to do both error correcting and error detection. And the number of consecutive bits they can detect is pretty large. Like consecutive mismatch bits, I think it's like 20 or 30. It's a huge number. So it would take a real huge, highly unlikely event so that you would read something, read it incorrectly, and it would still match the checksum. So it just didn't make sense to me. So I set up a test in 2019 with an old Mac and 15 drives. And I had 2 volumes on these 15 drives, 2 RAID 5 volumes. And the first one was active and the second one was passive, because they had 2 hypotheses. One was we're reading and writing and it's getting corrupted somewhere in the read and write path. And the other was, yeah, the CERN guys really know what they're talking about, and the data just sitting on the disk drive is magically degrading. So this was a whole bunch of large files. I think they were 2 gigs, I can't remember. But, and then, so the active reading and writing would just literally be randomly writing new files. Each file has a header with a random number seed in it, and then so I can tell what the random number should be or what the random data should be. And the passive volume is just sitting there, and every 10 days I go through, and it's a RAID 5 volume, so I just go and check the parity for both volumes, and it was, you know, we ran this after I came here. I'd done it for 6 months and hadn't detected any incorrect parity, with one exception, which I'll describe. So when I went back, I just let it run for another 12 months. And what we did was we ended up transferring 21 petabytes of information, 3 billion IOs. This is 100 times more than the CERN experiment. We saw 1 incorrect parity event, and that happened as a result of the power going off while I hit the wrong circuit breaker in our office, and the power got dumped on the test machine, and when I brought it back up, the next verify failed. But that was it. So I think what was going on with CERN was like over a network. There was a hardware RAID controller. There was a lot of networks, probably a lot of switch. I think somewhere in there, they were introducing data corruption. So the take-home lesson is, I don't think you need to worry about bit rot, but I do think you need to be on the lookout for data corruption through some sort of active process. So, you know, you should, if you have some way of auditing your systems for some sort of data corruption, I highly recommend you to do it. I actually found something similar to this. Again, I don't think it's bit rot because of the ability to check some data, but it is a data corruption event. I was looking for data corruption on volumes, and so I was doing a test where I was copying a 200 gigabyte file from the desktop onto a RAID 0 volume on a Thunderblade, and then I would do a comparison. And lo and behold, on one of these devices, I was getting a mismatch every time I ran the test. And so, as I say, I don't think it's bit rot. I don't think it was actually data being stored incorrectly, but there was a problem. And I went to our hardware engineers, and they said, oh, yeah, that's a problem we know about. He said, have you opened that Thunderblade? And I said, yeah, we swap blades all the time. Keep in mind that the Thunderblade has the blades and the CNC enclosured heatsink, and between the two is what's called a thermal pad, which is sort of like a sticky, it looks like foam, it's not quite, but it's this material that transfers heat really well, but it's sticky. So if you open it a little bit rambunctiously, what happens to those blades? They flex. And when they flex, what happens is there's a mechanical damage that happens that just makes them so that when you're reading and writing data, things get corrupted, and that is exactly what happened. We put new blades in there. There wasn't a problem. And the people in Taiwan in the hardware lab said, yeah, this is a known problem with blades. So the take-home lesson is, if you're dealing with blades, be careful with them. They look like, oh yeah, I could stick them in my pocket. Oh yeah, if they're not fitting, I can just force it a little bit. Don't do that. They're really delicate. Each of those chips is, I can't remember, 120 or 196 layers of silicon. There's a lot to go wrong. And the feature size is really small. Just be careful with them. And if you think you've got a problem or you want to test it, you can either test it using the software certify feature, which will write out a pattern and read it back, or you can just make a really big file and copy it over and use the CMP command to diff it with the file you copied over. If there's a problem, you're going to see it pretty easily. Certainly, if it's caused by mechanical problems with the blade. I now want to go through and do a quick review of the last 15 years of data loss. Where have we come from? Where do we have left to go? When we first started or not, actually in 2008, we've been shipping SoftRaid for 6 years at that point. Roughly 1 out of 100 people per month were losing volumes due to, we only supported RAID 0, just like Apple RAID only supports RAID 0 still to this day. And 1 out of 100 people were losing data due to a disk drive failure, and 1 out of 3,000 people was losing data every month due to user error. They'd go into SoftRaid, they'd hit a disk, and they'd initialize it, but it was part of their volume, and poof, there went all their data. Sort of a problem. So the first thing we did was we added a feature in SoftRaid that made it so that if you created a volume, it would get all the disks would get what we call the safeguard. Actually, the volume would get a safeguard. And so if you tried to do anything with any of the disks that were associated with that volume's data, like initialize them or zero them or anything like that, SoftRaid would prevent you from doing that. We couldn't prevent disk utility from doing that. But we did, I think we only have one case in the last 10 years of someone using disk utility to wipe out a SoftRaid volume, but we could prevent you from doing it in SoftRaid. So that was a huge win for us, but we're still losing volumes due to the fact there was only RAID 0. So in 2014, we introduced RAID 5, and poof, away went all the disks, the volume loss due to disk failure, which is exactly what you expect. That's what RAID 5 is supposed to protect you from, right? So now we have this useless graph because these numbers are so small. I mean, it doesn't make any sense. So we're going to just zoom in by a factor of 50, and this is what we see. Okay, there was this event right here is that one person who used disk utility. We were seeing a lot of loss due to all the disks on a volume disappearing. We saw some from disks changing position. So a machine would go to sleep, and when it woke up, what the operating system thought was this disk actually pointed to this disk and vice versa. Obviously, if you have a RAID volume and two disks swap position and you write to it, you're sort of toast, right? And that's exactly what was happening. It was an operating system bug. In macOS 10.12.1, they fixed the major problem which caused a whole bunch of disks to disappear at once. And then subsequently, in SoftRaid 5.6, we figured out that Apple was not going to fix this problem of disks swapping their position anytime soon. So we had reported to them, nothing happened. So we put in code in SoftRaid where we detected this event happened when you came out of sleep. We detected when you came out of sleep. And the first thing that we did was we read our own metadata on each drive and made sure it matched what we had in memory for that drive. And if it didn't match, we write protected the volume. And we put up a warning dialog telling people to restart. And all of a sudden, those problems went away. People stopped losing data. It was wonderful. Thank you very much, because Mark was the one who really pushed us to do that. We also saw a significant number of people, not significant, but every time there was a software update from Apple, there'd be a certain number of people who would lose their volume after software update. We reported that to Apple, nothing much happened, and then 2 years later, macOS 12 came out, and all of a sudden people stopped losing data after software updates. So something was happening in the software update process where the volume was not getting shut down correctly, and when you came back up, you had a volume that you had to use disk utility to get it to work. Not disk utility, sorry, disk warrior to get it to work. So let's go on to a real-life example. When I, a couple months ago, I was thinking about volume loss. When we have a customer they've lost a volume, we work pretty hard to recover it for them. And I asked customer support people, what do you think is going on? And they almost uniformly said, well, it seems to be associated with sleep. And I thought, this is sort of weird. Why is sleep causing people to lose volumes? And then we had this customer who got really irate on social media. I just bought this OWC thing. It's a piece of crap. You shouldn't get it. And they weren't even using SoftRaid. They were using our little 2-drive hardware RAID enclosure. And they swore up and down they were using APFS on that enclosure. Come to find out they were using exFAT. What do we know about exFAT? No journal, no ability to roll back to a previous metadata like APFS has. So you basically are running without a seatbelt, right? If you've got an exFAT volume and you unplug it while it's mounted, especially if you're writing to it, there's a good chance when you plug it back in, there's not going to be anything left. And so that was sort of our idea, possibly what could be going on. But so he had bought 2 of these. He was working on some video project. These were his ingest drives. He had one was his ingest and one was his backup. And so he sent in one. And then a week later, he had the same thing happen with the second one. And I thought, this is not a coincidence. There's something here we should dig into. We know that it's exFAT is part of the problem, but there's something else going on. So I started digging into it, and I realized, and I started talking to people, and I realized this is a notification that people get a lot of times coming out of sleep. And if one of your customers, or one of the people on a Mac that you're responsible for, gets this, take it seriously, because there's something wrong, okay? And I will describe what's actually going wrong under the hood, but you should do something with that person so that they don't get to the state. And that means either making it so their machine doesn't go to sleep, or getting it so that they unmount their volume before their machine goes to sleep, or having them shut down instead of having their machine go to sleep. So this whole idea of I'm going to leave my machine sleep overnight, not a good idea. I'll go through the exact situation where this happens so you know exactly what you're looking for. So Apple, in the old days for the first Macs, you'd be working on a document, you get a phone call, and you'd talk for an hour because it's your mom or your sister's birthday or something, and you come back and your Mac would be dead because the batteries didn't last very long back then. And you'd start it up, and everything that you had worked on was gone, right? It was all in memory, you forgot to save it, and you were in your last 4 hours of work. So Apple came up with this idea called Hibernate, and what Hibernate is it takes the entire image of what's in RAM and writes it out to a disk. And then when you start up again, it reads that image and plops it back in memory and restarts everything. Magic, great, okay? It's really cool and saved a lot of people from a lot of headache. The other thing that happens is Apple said, oh, well, we should also unmount all external storage because someone might unplug that device and take it somewhere else, and if they did that, it would be an unclean unmount if we don't unmount it when we go into Hibernate, right? So this is all very well and good, and it was written for all the SATA drives that were around at that point. And this is what actually is happening, and the root cause of why this guy lost his data. So over here we have all the events that are happening and all in the kernel, right? We start with the RAM image being saved, then the disks get, basically, they disappear. They get torn down, the volume gets unmounted, and the power gets turned off. What's wrong with this picture? Oh yeah, we're getting rid of the disks before you unmount the volume, right? So what do you do when you unmount a volume? You flush everything that's in the cache, right? You flush all the metadata as well, and then you mark the volume as cleanly unmounted. So all these writes that are happening right here where the volume's getting unmounted, guess where they're going? Nowhere, thank you very much. They're going to the bit bucket in the sky. And so what happens when you come back up, the power gets turned on, you restore the RAM image, your disks reappear, and then the file system goes and reads those disks, expecting to get hey, this volume is really cool, everything's fine. And what does it get instead? It gets, hey, this volume is not okay, I need to do recovery on it, I need to do FSCK and replay the journal and all sorts of things and put up this warning dialog. So the take-home message here is, this is something, if you see this notification, you need to take seriously. This is on SATA volumes. What happens on NVMe? Well, the NVMe driver writers thought, nobody's ever going to use NVMe on anything but an internal drive, right? So they just basically blow off the whole Hibernate thing altogether. And they just leave their volume in place and the drive in place, the disks in place, and it just all happens. It gets saved in the disk image, the RAM image, and then restored from the RAM image, and it's completely transparent. And so if you have a Thunderblade or something else that's NVMe, you don't get affected by this. pretty cool, right? Except most of us are using hard drives for large storage capacity, backups. Oh my God, backups. You know, and so it's a problem. And that's it. Thank you very much. So in closing, just a minute. In closing, if you got storage which is SATA, do something to keep yourself from getting to hibernate, and for all the machines you manage, because it will really help you. So.
Thank you, Tim.